The following question reads that a 0.17 gram sample of group 14 chloride XCl4 reacted with water to produce an oxide XO2 and HCl. And they've given you an equation. We don't know what X is. What we just simply know is that it's a group 14 chloride. That's the only information that's provided. It then reads that the HCl produced was absorbed in 100 cm cube or 0.1 mole per dm cube sodium hydroxide and excess. So here is the HCl that has been produced reacting with the excess NaOH, and I can tell you exactly what amount of NaOH that's being used in this reaction. It's 100 cm cube of 0.1 mole per dm cube NaOH. What we can do over here is we can use the formula N is equal to C into V, which is concentration multiplied by volume, gives you moles. And over here the volume should be in dm cube, so it's 0.1 decimeter cube. So the moles that you're going to have, the moles of NaOH that are added over here, it's going to be 0.01 moles. So you're reacting the HCl produced by 0.01 moles of NaOH, which is in excess, which basically means that some of this NaOH will not react or would be left over. So I did N is equal to C into V, concentration multiplied by volume, concentration multiplied by volume, which should be in dm cube, divided by 1000, I got 0.01 moles. In the next part, in a titration, the unreacted NaOH, so the NaOH that is left over from this previous reaction is now being, this unreacted NaOH is now being reacted or required 30 cm cube, 0.2 mole per dm cube HCl acid for complete neutralization. So what's happening is that the unreacted NaOH that did not get used up in the previous reaction is now again being reacted with the HCl, and you're given the volume and the concentration of this HCl solution. So I can use the formula again, concentration multiplied by volume, and figure out the amount of HCl that is being used in this titration over here. So it's 30 cm cube into 0.2, and this should be divided by 1000. So my answer comes out to be, so it's coming out to be 0.006 moles. So that is the amount of HCl that is required to finish off the unreacted NaOH in the previous step. So we just need to solve I've already solved some of the parts. So now what we're going to do is we're going to solve the complete question, going step by step. The first part, option A, is you need to calculate the amount in moles of HCl used in the titration to neutralize the unreacted NaOH. So this unreacted NaOH over here, I've already done the calculation. I figured out that the amount of HCl that's being used for that unreacted NaOH is 30 cm cube into 0.2 mole per dm cube. I just need to add the working over here. So 30 divided by 1000 dm cube multiplied by 0.2 mole per decimeter cube. My answer comes out to be 0.006 and 0.00 moles. Now moving on to the next part, part B. We now asked to, in part B, we're asked to write the equation for the reaction between HCl and NaOH. So it's a simple reaction between an acid and a base producing salt and water. So I've written it down. So HCl plus NaOH produces NaCl and H2O. What is important is that you must realize that the ratio between HCl and NaOH in the equation is 1:1. So the amount of moles of HCl in the previous step that we recorded over here, the amount of moles of HCl and the amount of moles of NaOH, it must be the same. And this is exactly what is being asked in the next step. You're supposed to calculate the amount in moles of NaOH neutralized by the titration. So going back to the first part over here, you will notice that the HCl at the end was being that was being used in titration was being used to react with the unreacted NaOH from the previous step. So the amount of moles of HCl and NaOH have 1:1. In the equation, it's 1:1. So if HCl has 0.006 moles, NaOH is also going to have exactly the same amount of moles. So the answer to that is going to be, and you're going to show some working as well in this particular part, part C. Moving to the next part of the question, part D, we are now asked to calculate the amount in moles of NaOH that reacted with the HCl produced by the reaction in equation 1. So let's go back and have a look. Remember, now he's basically asking us that the HCl that was produced in reaction 1 or equation 1, this HCl over here, reacted with NaOH. And that NaOH was in excess. And we also did some calculation. We figured out that the HCl produced was absorbed in 100 cm cube or 0.1 mole per decimeter cube NaOH, which was in excess. And using the formula concentration multiplied by volume, we were able to figure out 0.01 moles of NaOH was being used in this reaction. And then you had this unreacted NaOH that was left over, and that was then reacting with 0.006 moles of HCl. Now, based on a previous calculation, using HCl's moles, we were able to figure out the unreacted moles of NaOH, which were coming out to be 0.006 moles. And now this is the unreacted NaOH or the leftover NaOH. Remember, we added 0.01 moles of NaOH in excess initially. So using these two values, this value and the unreacted NaOH, and going back to the question, so this is what we have. This is the excess NaOH that we added initially in equation 1, which was 0.01 moles. Then you had leftover NaOH, which was neutralized by titration. That NaOH came out to be, the leftover NaOH was 0.006 moles. So what was the amount of NaOH that actually reacted in equation 1? You're going to subtract the two values. This is the amount that you added, and this is the amount that is left over. And if you subtract the two values, it's going to be 0.01 minus 0.006. And your answer is going to be, so on my calculator, this value comes out to be equal to 4 times 10 to the power minus 3 moles. So that is the amount. Let's go back. So that is the amount that I'm going to put 4 into 10 raised to the power minus 3 moles over here. So that is the amount of moles of NaOH that actually took part in the reaction, not the excess amount, but the amount that took part in the reaction. So let's go back and have a look on the next part of the question, which is, we now need to calculate the amount in moles of HCl produced by the reaction in equation 1. So according to our equation, we still know that NaOH and HCl react in 1:1, which is they react in equal ratio. So going back to our original equation, so the HCl that is produced in this reaction reacted with this amount of NaOH, and I know that the ratio is the same. Although this is a separate equation, but the HCl that is produced in this reaction and the amount of NaOH that's reacting with it, it's going to have 1:1. So the amount of moles of HCl would be exactly the same. It's going to be 4 into 10 to the power minus 3 moles. So this is what we are going to add over there. So the amount would be 4 times 10 to the power minus 3 moles. So that is the amount of HCl that is produced in equation 1. And in the next part, part F, you now need to calculate the amount in moles of HCl4 in the original sample. So let's go back to our reaction. And we have reached this part. We figured out that the amount of moles of HCl we are now known, it's 4 into 10 to the power minus 3 moles. So using this amount, we can figure out the moles of HCl4. And you can notice that the ratio is 4 HCls are produced by 1 HCl4. So it's 4:1. So if it's 4 into 10 to the power minus 3 moles of HCl, then the amount of HCl4 that would be required for producing that, according to this ratio, would be 1 into 10 raised to the power minus 3 moles. Because it's 1:4 in the equation. So 4 times 10 to the power minus 3 moles would be produced by 1 times 10 to the power minus 3 moles of HCl4. So let's go back and answer our question. So I've copied the ratio. HCl and HCl4 have a ratio of 4:1. So 4 times 10 to the power minus 3 moles, X would come out to be equal to 1 times 10 to the power minus 3 moles. So we're done with this part. We figured out the moles of HCl4 and we also know the mass. So in the next part, calculate the molecular MR of HCl4. So we can use the formula moles is equal to mass divided by MR, and the MR is unknown, but we know the sample's mass, which is 0.17 grams. It's given over here. and we also know its moles. So what we're going to do is we're going to make MR the subject of the equation. So it's going to be mass, which is 0.17 grams, divided by the amount in moles, which is 1 times 10 to the power minus 3 moles. So using this, we would be able to calculate the MR, which comes out to be equal to 170 based on this calculation over here. And the next part, part H, is you need to calculate the relative atomic mass AR of X and suggest its identity. We know that, so far what we know is that the MR of XCl4 is 170. It's given over here in the last part. So the MR of XCl4 is 170, which basically means the MR is basically the sum of the atomic masses, or the ARs. X is unknown. There are 4 chlorines, which is going to be 4 times 35.5, which is the AR of chlorine, and that should sum up and be equal to 170. And using this, we can make X the subject of the equation, and X value of X would come out to be, so it's according to my calculator, it's coming out to be equal to 28. So the AR of X is 28. What you just need to do is now look at the periodic table and find what is found at proton number, or AR atomic mass, of 28, and the answer would come out to be equal to, it's going to be silicon. Silicon is the element that has an AR of 28. The following question states that for many compounds, the enthalpy change of formation cannot be calculated directly. An indirect method based on enthalpy change of combustion can be used, which is based on the Hess law. The enthalpy change of combustion can be found by a calorimetry experiment in which the heat energy given off during combustion is used to heat a known mass of water and the temperature change recorded. So the first part is explain the meaning of the term standard enthalpy change of combustion. So enthalpy change of combustion is it's the energy released when 1 mole of a substance completely burns in excess oxygen, and it's measured under standard conditions. Since the term standard is being used, you need to add that it is being measured under standard conditions, which are 25 degrees centigrade, temperature 1 atmospheric pressure, and if it's a solution, it should be 1 mole per decimeter cube. Moving to the next part of the question now, we need to write the equation for the complete combustion of ethanol. So here's your equation. Ethanol, when it burns with oxygen, it produces carbon dioxide and water. And we have balanced the equation as well. There are 2 carbons through 2 CO2s, the 5 plus 1, 6 hydrogens over here. So that's 3 water molecules. And there are 4 plus 3 oxygens over here. So 7 oxygen in total in the products. So you have 6 plus 1 oxygen over here. So that's 7. So this is a balanced equation. To the next part of the question, it says that in an experiment to determine the enthalpy change of combustion of ethanol, so 0.23 grams of ethanol was burned and the heat given off raised the temperature of 100 grams of water by 16.3 degrees centigrade. So this is the information that's provided, and you're supposed to calculate the heat energy change Q during the combustion of 0.23 grams of ethanol. So I'm going to use the formula Q is equal to mc delta T to figure out the energy change. So I have 100 grams of water. That's the mass of water. So I have 100 grams of water. So this 100 grams of water is absorbing all the energy that is being produced when ethanol is being burned. So all the energy from ethanol combustion is being absorbed by this 100 grams of water. So I'm going to figure out what amount of energy is absorbed by 100 grams of water. So the mass of water is 100. The specific heat capacity C is given in the data booklet. It's given as 4.18 kilojoules, 4.18 joules per Kelvin per mole, and the temperature change delta T is given as 16.3. So delta T is provided as 16.3. It's written over here, 16.3. And what you need to be very, very careful is you need to heat is given off. So it means it's an exothermic reaction. So exothermic reaction, you need to understand that the sign of the energy has to be, you need to add the sign of energy yourself. So it's an exothermic reaction. So put a negative sign over there, which would indicate that it's an exothermic reaction. And the answer that I'm getting for this value is coming out to be 6813.4 joules. And it has to have a negative sign. It's an exothermic reaction. So this is the amount of energy that is being absorbed by water when ethanol is burnt. So moving to the next part, The next part is we need to calculate part 2. Calculate the enthalpy change of burning 1 mole of ethanol. Include a sign in your answer. So what we have so far figured out is that 0.23 grams of ethanol were burnt. And what is the amount of energy that was produced? The amount of energy that was produced was minus 6813. So minus 6813.4 joules of energy was produced. So I need to figure out what would happen if 1 mole of ethanol is burnt. So the first thing is I need to figure out what is the moles of ethanol that were burnt that produced this much energy. Now moles is mass divided by the MR. The MR of ethanol is 46. It's C2H5OH. So you can figure out the MR, which is going to be 2 carbons, that's 24, plus 1 oxygen, that's 16. So it's 40 plus 6 hydrogens, that's 46. So 0.23 divided by 46. So 0.005 moles, this 0.23 divided by 46 is 0.005 moles of ethanol produces this amount of energy, and we are being asked to figure out what is the energy produced by 1 mole of ethanol. So what we're going to do is we're going to use simple ratios. So 1 mole of ethanol produces what amount of energy? So we're going to use X as the unknown. So ratios, 0.05 moles produces this much energy, 1 mole of ethanol produces what amount of energy, and we are going to cross multiply. And if we cross multiply a value of X, the unknown comes out to be equal to minus 6813.4 divided by 0.005, and the answer should be given in kilojoules. So the value that I'm going to get for this is, in my calculator, it's coming out to be minus 1362.7 in kilojoules. Remember, this value was in joules, so you need to divide it by 1000. Whatever the answer, it's going to be divided by 1000, and your final answer is going to come out to be equal to minus 1362.7 kilojoules per mole. So that is the amount of energy that is produced by 1 mole of ethanol. Let's move to the next part of the question, part 3. We're now being asked suggest 2 reasons why the value for the enthalpy change of combustion of ethanol determined by a simple laboratory calorimetry experiment is likely to be lower than the true value. So the first reason is that there is going to be significant heat loss to the surrounding, or to the air, or to the containers, to the surrounding environment. As you can see over here, this was an experiment. We were heating 100 grams of water and we were providing it with energy, but a lot of energy, not all of the energy is going to go into the water, or is going to be gained by the water. A lot of the energy would be lost. It's going to be lost to the surrounding, or wouldn't even reach the container. So that energy loss is going to, because energy is lost, so your calculated energy for this container, for this the energy absorbed by water is going to be lesser. So your value, your eventual value, your answer is going to be, it's going to be lower than the original value. Other 2 reasons that I can think of is that ethanol might not completely combust, because if you're heating or burning ethanol, a lot of ethanol, because it has a low melting and boiling point, might evaporate, or simply just evaporate and mix with air, and would avoid combustion. So ethanol might not completely combust. So, or it could also be that ethanol may be impure. There might be a lot of impurities in ethanol. So the heat energy produced would be lesser because the impurities might not combust. Now the next part of the question, part C, is the table gives some enthalpy change of combustion values. So the standard enthalpy change of combustion values are given for the following substance: for carbon, for hydrogen, and for this is propanol. Now construct a labeled energy cycle to show how these values could be used to calculate the enthalpy change of formation of C3H7OH. So we have this reaction, and we need to figure out the enthalpy change for this particular reaction. And what the question is asking us to do is to use Hess law and create another path for this particular reaction, and use that path to measure the enthalpy change for this reaction. That is what Hess law is. That one path has the same energy changes as the other path, as long as the starting point and the end point are the same. So we need to create another path using the information that's provided over here, and we're going to create another path and figure out the enthalpy change for the following reaction. So let's go back, and now I'm going to start constructing the cycle. Let's look at the first one. The enthalpy change of combustion of carbon is given. The reaction is that carbon reacts with oxygen, combusts, and produces CO2, and the enthalpy change for this particular reaction is given as minus 393.5. So I'm going to use this reaction first. These are my reactants, and as you can see, they are carbons over here. Now, carbon is going to combust. It's going to react with oxygen, and it will get converted into carbon dioxide. And the enthalpy change for this arrow over here is going to be, if you go back and have a look, you would notice that there is carbon combusting, so that's minus 393.5. But in the enthalpy change of combustion of carbon, there's only one carbon. Whereas in our equation, we are combusting three carbons getting converted to 3 carbon dioxide molecules. So the enthalpy change minus 393.5 is going to be, so this is minus 393.5, but it's going to be multiplied by 3 because you have 3 carbons that are undergoing combustion. So that's the first part. I've connected this. Now moving to the other part, you're also given the enthalpy change of combustion of hydrogen. Enthalpy change of combustion of hydrogen is when hydrogen burns with oxygen, half O2, and it produces H2O. So the enthalpy change of combustion of 1 mole of hydrogen is given as minus 285.8. So this value is also given. So we have hydrogen over here as well. So I've already combusted 3 carbons. I'm going to combust the hydrogens. 4 hydrogens are going to produce 4 H2O molecules. So this is also done in this step. And the enthalpy change for combusting 4 hydrogen is, for combusting 1 hydrogen was minus 285.8. So minus 285.8 would be multiplied by 4. So this is going to be the enthalpy change for combusting 4 hydrogen. This is the enthalpy change for combusting 3 carbons. We're not going to combust oxygen because oxygen does not undergo combustion. Let's look at the third part now, which is the combustion enthalpy change of combustion of C3H7OH. That's given as minus 2021.0 kilojoules per mole. So the enthalpy change of combustion of propanol is propanol burning produces 3 carbon dioxide and 4 water molecules. So it is this part over here. Propanol combusts, produces 3 carbon dioxide and 4 water molecules, and the enthalpy change for this reaction is given as minus 2021 kilojoules. So minus 2021.0 kilojoules per mole, and I'm going to multiply it by 1 only because we just have 1 propanol in our equation. So the Hess cycle is now complete. This was my first path. I needed to figure out the enthalpy change of formation of propanols. This is one path, and the other path is you move from this point to this point and from here to here. So this is my other path that has been created. So to find the enthalpy change of formation, I'm going to follow this orange arrow that's given over here. This is the first part, enthalpy of formation. So enthalpy of formation is going to be equal, this path is going to be equal to this other path. So going from here to here, that is minus 393.5. But that would be multiplied by 3. Then going from here to here also includes combusting hydrogen. So that's minus 285.8. So that's minus 285.8 multiplied by 4. And then this enthalpy change over here. You've reached this point. Now you're going to go to this point and form the products. This point is you have to go in the opposite direction. So it's not going to be minus 2021. It's going to become plus 20 and 21. So it's going to be plus 2021 kilojoules per mole. And I'm going to use my calculator to find the value of this enthalpy change of formation now. So this is the answer that I'm getting. It's coming out to be minus 302.7 kilojoules per mole. So this is the enthalpy change for this reaction over here. So we used Hess law and we created the Hess cycle. This is the first path, and then you follow this path and you get the enthalpy change of formation. Now moving to the next part of the question. The next part of the question is, it is actually, we've done the next part as well. Calculate the enthalpy change of formation of C3H7OH, which we have just done over here. It's minus 302.7 kilojoules per mole. The first part wanted us to construct the Hess cycle. We constructed the Hess cycle, and the second part wanted us to calculate the value of enthalpy change of formation, which we have already done. The following question reads that the elements in group 2 and the compound show various trends in their physical and chemical properties. The graph below shows the radius values of the atoms and plus 2 ions of the elements in group 2. So the atomic radius is given. The atomic radius of the atom would be bigger. For the ion, it's going to be lesser because the ion would lose electrons, would lose the outer shell electrons. So group 2 elements are going to lose 2 electrons. They're going to lose 2 electrons, and they would lose their they're going to lose their outer shell. So they are going to be smaller. The ions are going to be smaller. The atoms are going to be bigger because they're going to have one more shell. Now moving to the next part of the question. The question is, explain why both lines show a steady increase in the values of the radii shown down the group. So the explanation for that is that atoms or ions become larger as you go down the group because the number of shells keep on increasing down the group. So I've drawn the diagram of the electronic structures of the first 2 elements. This is beryllium with 4 electrons. So it's 2 in the first shell, 2 in the second shell. This is Mg with 12 electrons. That's going to be 2 and 8 in the second shell. And they're going to have 2 in the next shell. So as you go down the group, the number of shells keep on increasing, so the size of the atom becomes bigger, and the size of the ion is also going to become bigger. It's going to have more shells as well. The next part of the question now reads that state and explain which line represents the atomic radius and which represents the ionic radius, which I have already discussed over here. The atomic radius is going to be bigger. The ionic radius is the one that's going to be smaller. For example, for beryllium, the ion would be +2. So if it is +2, that would indicate that the outer 2 electrons would be lost. Metals always lose their outer electrons. So if I remove this, if we rub this off, these outer electrons are lost. So you can see without the outer shells, the ion is much smaller. The same would apply to Mg as well. If we get rid of the outer 2 electrons, Mg is a metal, it's going to lose the 2 outer electrons as well. So Mg +2 over here lost its outer electrons. The ionic radius is going to be smaller. So for the upper line is for the atoms. This is Mg, the atom, and this is Mg +2, the ion. So they lose the outer shell electrons. This is what we are going to write over here for its explanation. So the answer is atomic radius is bigger than the ionic radius as group 2 metals lose their electrons and lose outer shells to form ions. And if they do so, so the ionic radius becomes smaller. So upper line was for the atomic radius. This is going to be my answer for this question. The next part is that L is a salt of group 2 element M, and when L is heated strongly, a brown gas is observed and a white solid remains. The white solid dissolves in water to form a colorless solution of metal MOH2, so it's a metal hydroxide that's formed. An addition of a dilute sulfuric acid to this color solution produces a dense white precipitate. So the first part is we need to figure out the anion in salt L. Now, if you look at the very first part, L is heated strongly and a brown gas is observed and a white solid remains. So this brown gas is probably going to be NO2. NO2 is a brown gas. And this is thermal decomposition that's happening. It is heated strongly, it decomposes to produce a brown gas. So what's basically happening is this represents the decomposition of a metal nitrate. Metal nitrate undergoes decomposition to produce this brown gas NO2. And the white solid is probably going to be the metal oxide that is so this is the white solid, the metal oxide that is produced. So the anion responsible would be the nitrate ion. We don't know what M is, but the anion would be nitrate ion because it decomposes to produce this brown gas. Moving to the next part of the question, we now have to identify the element M and write an ionic equation for the formation of the white precipitate with sulfuric acid. So let's go back. Now, if you look at the description of L, you will notice that it underwent decomposition after strong heating. And the white solid that is produced, which is the metal oxide, it dissolves in water to form a colorless solution of the metal hydroxide. Now, this white solid is going to dissolve, and the solubility of the hydroxide or oxides, it keeps increasing down the group. So it's forming a colorless solution when you dissolve it in water, which basically indicates that it's if you dissolve it in water, it forms a solution of a metal hydroxide, which probably indicates that it's a very soluble group 2 hydroxide, probably barium oxide. This must probably be barium oxide. So if this is barium oxide and it reacts with water to produce BOH2, then barium ions, the test for barium ions is that you add sulfuric acid. If you add sulfuric acid, a white precipitate forms. So BOH2, since it's aqueous, which means that it's going to dissociate in aqueous state. And if you add sulfuric acid, which is also aqueous, the ions would be in dissociated form. If you add them together in a beaker, what's going to happen is that the insoluble precipitate, barium ions and sulfate ions, would get together to form an insoluble precipitate of BaSO4. So that would be produced and the ions would get removed from the solution. And this is what's happening. If you add sulfuric acid, the ions would get together to form a dense white precipitate. So barium sulfate is getting produced. So the most probable answer for this is, because it has a very soluble oxide, it forms a colorless solution, and because it also forms a precipitate with sulfate ions, so it's probably going to be barium sulfate, and the metal in L is going to be group 2 metal would be barium. So M is barium, and the equation is going to be barium hydroxide plus sulfuric acid to form this barium sulfate dense white precipitate, and a water molecule will be produced with it. The next part C of the question is, give the formula of salt L and use it to write an equation for the thermal decomposition of salt L. We have already done this partially. The original L was a nitrate because it decomposed to form a brown gas. So it's barium nitrate now, and we can write down the equation. It's going to be barium nitrate decomposing to produce a white solid, which is going to be barium oxide plus 2 nitrogen dioxide gas molecules plus half molecules of oxygen gas. So this would be my equation. Now moving to the next part of the question, you're now given calcium carbonate and calcium hydroxide can both be used in agriculture to neutralize acidic soils. Write an equation for the neutralization of acid by each calcium hydroxide and calcium carbonate. So I've written down the equation: calcium hydroxide reacting with an acid, and it's going to produce a salt and a water molecule. It's a base plus acid reaction. I've written down the ionic equation. I have not mentioned specifically because the question was not mentioning which acid was being used. It was just acidic soil. We didn't know what the acid was. What you can do is, when you're trying to write this equation, think of an actual acid and write an equation using that actual acid, and then remove the spectator ions. So for example, over here I've used calcium hydroxide with an actual acid. They didn't mention any acid, so I've used Heatseal. Calcium hydroxide with Heatseal produces calcium chloride and a water molecule, and I've balanced it. What you can simply do now is, because the acid is not specifically mentioned, you just know that acids have H+1 ions. You can write down you remove the spectator ion. Cl-1 would be a spectator ion, that would leave you with 2H+1. Cl-1 is a spectator ion, that would leave you with +2. So if you get rid of the spectator ion, you're going to get this equation over here. The same could be done with calcium carbonate reacting with an acid. It's going to produce a salt, a water molecule, and carbon dioxide molecule. So you can think of calcium carbonate reacting with 2 molecules of HCl, producing calcium chloride, water, and H2. And you can just get rid of the chloride ions because they are spectator ions. Next part of the question is, suggest and explain why calcium carbonate is a better choice than calcium hydroxide for the purpose in areas of high rainfall. So why is calcium carbonate a better choice? So the answer to that is that calcium carbonate is not very soluble. It's not soluble. You add it to soil, it's not going to get washed away with the high rainfall. But calcium hydroxide is partially soluble, and it is going to get washed away if there is rain. So that's the answer to this question. And the next part is that magnesium reacts with both cold acid and steam. Give the formula of the magnesium containing product of each of these reactions. So for cold water, when magnesium reacts with cold water, it's going to form magnesium hydroxide plus it's going to give off hydrogen gas. But the problem with steam is that it's going to be the same equation, but with steam is you're taking the temperature, you're increasing the temperature. If you increase the temperature, you're going to get the same exact equation. But the issue is going to be that if you increase temperature, what's going to happen is that the magnesium hydroxide would decompose. It's going to decompose to produce magnesium oxide and give off a water molecule. So instead of getting magnesium hydroxide because of the higher temperature, you're going to get magnesium oxide. So your answer to both questions would be, in the first one you're going to get magnesium hydroxide, and the second one you're going to get magnesium oxide instead of magnesium hydroxide. The following question reads that in each section of this question an organic compound is shown. For each compound, give its name and answer the question about it. So this is the molecule, and we need to first name it. I'm going to quickly draw this molecule. And I'm going to quickly draw this molecule without the hydrogens, because hydrogen atoms just make things confusing. So it's 1, 2, 3 carbon atoms. So it's 1, 2, and 3 carbon atoms. And then with this carbon atom, there's a carbon branch. So that's CH3. And after that, there's another carbon atom in the chain. So that's another carbon atom. Then you have a double bond, and then you have another carbon atom and another carbon atom. So I'm not drawing all the hydrogens. Next part is I'm going to have, this is going to be my longest chain, and this would be my branch. Now this longest chain has 1, 2, 3, and then there's 4, 5, and 6 carbons. So it's 6 carbon atoms. The longest chain, main chain name would start with hex. Hex means 6. And there's a double bond. That means it's an alkene. So it's going to be ene. And the double bond is remember, double bond has a higher precedence. So I'm going to count the double bond from the side that gives the smaller number. So I'm going to count it from this side. So this would be carbon number 1. So carbon 1 and carbon 2. So the double bond is at carbon number 2. So it's going to be hex 2-ene. And then I have a carbon branch, a methyl branch. It's only one carbon. It contains one carbon. So the branch is going to be named methyl. Only one branch, and I have to tell the position of that branch. The position of that branch is, remember, I'm counting from this side. I'm giving double bond the smaller number, so it's going to be 1, 2, 3, and it's on the 4th carbon atom, so it's going to be 4-methyl hex 2-ene. So that's the name of this molecule. The next part is, this compound shows stereoisomerism, and we need to define what is meant by stereoisomerism. The definition of the term stereoisomer is that the molecules having the exact same structural formula. The bonds are connected in the same way. They have the same connectivity, but the orientation, they're going to have different orientation and arrangement of bonds in space. So one bond might be pointing upwards, and the other molecule, the bond would be connected to the same atom, but it would be pointing in a different direction. So that is what is meant by stereoisomers. Now, part 3 is state and explain how many stereoisomers of the structure there are, and we have this structure in front of us, this structure that I've drawn over here. Let's redraw this structure over here, and let's mention how many different types of stereoisomers the molecule could form. Now, if you have drawn the molecule, now if you look at this molecule carefully, you would notice that it forms two types of stereoisomers. One is formed by this double bond over here. It's going to have a cis and trans version, because if around the double bond, if the carbon atom in the double bond is bonded to two different groups, over here there's the two different groups attached, over here as well the two different groups attached, one side there's H and the other side there's this entire carbon chain, then it's going to form cis and trans isomers. So I'm going to draw the cis and trans isomers of this molecule. Remember, when the carbon is forming double bonds, the arrangement is going to be trigonal planar, or it's going to be fan shaped, and the angles would be 120 degrees. So I'm going to draw the first cis version probably for the molecule. I've drawn the double bond. On one side there's H, and on the other side there is CH3. So I'm going to draw that, but with a 120 degree angle. So that's H and CH3. And on the other side again I have an H, and on the other side I have this carbon chain. So there's going to be H. And on the other side I have this carbon chain. It's going to be CH with a CH3 branch. Then you're going to have CH3 and CH2. So I've drawn this side over here, CH3, CH2, then CH and a CH3 branch. Then it's attached to this carbon double bond carbon. So So this is one arrangement around the double bond. And remember, rotation is not possible around the double bond. The other molecule is going to have exactly the same arrangement, connectivity, but except for the fact that over here both H are pointing upwards, but in the other molecule, this side is going to switch. The H would be the one that would be pointing downwards instead of pointing upwards. So this over here is my other version where instead of the H pointing upwards, the H is pointing downwards, and this would be my cis version, and this is going to be my trans version. So I'm going to have two different stereoisomers, geometric isomers. One is cis and the other one is trans. The other type of isomerism, stereoisomerism, it's going to show is there's a chiral carbon atom. This carbon atom over here is chiral. Remember, carbon atoms, when they are forming single bonds, it's going to be tetrahedral, and angles would be 109.5 degrees. And if it's bonded to four different groups, on all sides there are four different groups, it's going to form stereoisomers. It's going to form two non-superimposable mirror images. So I'm going to draw those two non-superimposable mirror images now. So this is the first three-dimensional arrangement of this carbon atom. It's tetrahedral. All the angles are 109.5 degrees, and I've shown all the groups: CH3 on one side, CH3 on the other side, H on one side, and there's CH double bond CH3 on the other side. So that's the first version, and then there's going to be a mirrored version of the same. It's going to be a non-superimposable mirrored version of the same molecule. So let's draw that as well. So these two over here are the mirrored versions of each other. This molecule is the mirrored version. The left and right sides have switched, and no matter what you're going to do, the two molecules, they're never going to look the same. They're non-superimposable. They look exactly the same, but they are different. The bonds are pointing in different directions, and no matter which way you rotate these molecules, one of the bonds is going to always point in a different directions. They're not always going to look exactly the same. Now, the answer that you're going to write in the space is that why are they forming cis-trans? Because you have two different groups attached to each carbon in carbon double bond carbon, so which is why you're getting a cis-trans isomer. And the other one is why are we having why are they forming optical isomers? Because there's one chiral, as it has four different groups attached to the chiral carbon atom. So that would be the answer to the question. Moving to the next question, now you have this molecule given, and we need to name this molecule. Now this molecule over here has a double bond, so let's first draw. It has a double bond, and then it also has two carbons attached to the double bond, and on both sides there are two CH3 groups over here as well, or on this side as well. So there are going to be two CH3 groups attached. So there are two CH3 groups attached to it. So the first part is naming this molecule. We need to identify the longest continuous carbon atom chain. The longest chain is going to be this one over here, and these would be the branches. If you look at the longest chain, it has four carbon atoms, so that means it's the prefix is going to be but. So you're going to start with but, and you also notice that the longest chain is an alkene. It has a double bond, so it's going to end with ene. So it's butene, and the double bond position on the longest chain is first and second carbon atom, so it's going to be butene. So we're done with the longest chain. Now we're going to focus on the branches. There are two branches, one carbon atom branch over here and one carbon atom branch on this side. So this is methyl and this is also methyl. So there are two methyl branches. I'm going to call them dimethyl. Dimethyl means I have two carbon branches, one carbon atom branch, methyl branch over here, one over here, and I need to number them now. The longest carbon atom chain was this one, and I was counting from this side, so it's first, and the second carbon atom there's a methyl, and on the third carbon atom there's a methyl, so it's going to be 2 and 3 dimethyl. So I need to mention the position of both methyl groups. So it's 2,3-dimethyl but-2-ene. That is the name of this molecule. Now the next part is we need to draw the skeletal formula of the organic product of this reaction of this compound with cold dilute acidified potassium magnate 7 ions. So if you take this molecule, so I've drawn this molecule. Now cold dilute acidified magnate 7 ions or KMnO4. This is mild oxidation that's happening. During mild oxidation of alkenes, what happens is whenever there's mild oxidation, the double bond breaks, and in its place you get a single bond. The double bond does not break completely. You get a single bond in its place, and a diol is formed. Both carbon atoms, they end up joining with OH. So a diol is formed as a result. So this is by product of the reaction, and I need to figure out the skeletal formula. Skeletal formula only shows carbons as tiny dots, as nodes. So this is one carbon, this is another carbon, this is another carbon, this is another. So they are these carbons connected in this manner. So I'm going to start with this one. So that's one carbon connected to another carbon, which is then connected to this carbon over here. So that's another carbon that is then connected to this carbon, which is then branched and forming connected to two other carbon atoms. So that is then branched, it's connected to these carbon atoms, and you have to show the functional groups that are attached. There are two OH groups attached to the middle carbon atom, so I'm going to show that. I'm going to show these two OH groups. So there's an OH group over here and an OH group on this side. The next part 3 of the question now states that name the organic product of the reaction of this compound with hot concentrated acidified magnate 7 ions. So let's look at this compound again, and let's redraw this compound. We're going to try and figure out the molecule, and this time it's hot concentrated. So we're talking about strong oxidation. Now here's my original molecule. Now strong oxidation is the double bond is going to break completely. And if it breaks completely and you get a carbon atom, a fragment of the carbon atom, if it's bonded to carbon chains on both sides, this particular carbon atom is converted into a ketone. It attaches to an oxygen. So the double bond is going to break. If the carbon atom is connected to two carbon chains, this carbon atom, this particular double bond carbon atom gets converted into a ketone. This is exactly the scenario that's going to happen over here. The double bond breaks and this carbon atom is connected to two carbon chains. So, and both sides are identical. It's a symmetric molecule. This carbon atom is exactly the same as well. It's bonded to two carbon chains and the double bond completely breaks. So this molecule over here is going to get converted into a, so there's CH3, CH3. The double bond has broken off, so it's going to be converted into a ketone. So both sides are going to produce the exact same molecule. What is the name of this molecule? It's a ketone and there are three carbon atoms, so it's propanone. So the answer to this question is going to be, it's going to be propanone. That's, they wanted us to name the product, so it's propanone. Let's move to the next part 4 of the question. Draw the structure of a part of a molecule of the addition polymer formed from this compound showing exactly 3 repeat units. So our molecule, let's draw this molecule. So it's an alkene. The first part is you need to be very careful. This is the original molecule. The double bond is bonded to CH3s. Remember, when you're drawing a polymer, this carbon atom is bonded to two CH3 groups. Remember, nothing to put on the right side. Don't put anything on the right side or on the left side of the double bond. Draw everything either take it to the top or take it to the bottom. So I have two CH3s bonded to it. So I'm going to take one CH3 and draw it on top, and the other CH3 would be drawn at the bottom. The same, it's also bonded to two CH3s. So I'm going to do exactly the same. So I'm not going to draw it like this. Don't draw anything on the right side or the left side. Just take things either to the top or to the left, to the bottom. So I've now drawn 3 repeat units. The question was asking us to draw 3 repeat units. So I've drawn 3 monomers, and under high pressures and high temperatures, they're going to get connect together. The double bond is going to break away. It's going to break off. It's going to turn into a single bond. So all of them are going to get saturated. They're going to get converted into a single bond, and these carbons, they would start connecting with each other, and there should be continuation bonds drawn at either ends to show that this chain is continuing. Now in the next part C, I have another molecule and I need to name this molecule. So let's try and name this first. So let's draw the molecule first. There is a double bond And if you look carefully, there are two hydrogens attached to this, and there are two CH3 branches attached to this carbon atom. So two hydrogens attached with this carbon and two CH3 branches attached. So there's a CH3 branch and there's another CH3 branch, methyl branch attached to this carbon atom. So I'm going to try and name this now. So the first thing is I'm going to pick the longest chain. This over here is my longest chain. The three carbon atoms, so that's prop. And there's a double bond over here. A double bond indicates that the name should end with ene. And it's on the first carbon atom, so it's prop 1 ene. Or you can simply call it propene because there is no other version of propene. The double bond on either side, it's going to be the same molecule. So it's prop 1 ene because the double bond is on the first carbon atom from the right. And there's a methyl branch attached. So there's one carbon atom branch attached. So there's a methyl branch attached on the second carbon atom. On this main chain, on the second carbon atom, there's a methyl branch attached. So it's 2-methyl prop 1 ene. Moving to the next part of the question, part 2. You're now asked to complete the mechanism for the reaction of this compound with hydrogen bromide and include all necessary curly arrows, lone pairs, charges, and partial charges. So we have to describe the mechanism. This is an addition reaction. Alkenes, the double bond, attracts electrophiles. So this molecule is going to get added to this double bond. Now the first thing is this is a polar molecule. So hydrogen is going to have a partial positive charge. Bromine is going to have a partial or slight negative charge, and there would be two electrons in this bond. Because of the repulsion from the electrons in the double bond, these electrons are going to get repelled further away. So these electrons over here in the bond are going to get repelled because of the repulsion from this double bond, and the electrons in the double bond, in the pi electron cloud specifically, these electrons are going to get attracted to this positive hydrogen. So in the next step, this bromine, it breaks away, Br-1 breaks away, and this H positive instead gets attracted to the electrons in the double bond. So now the H positive is going to get attracted, and the double bond over here, the pi electron cloud over here, will be attracted by this positive hydrogen. So these electrons get attracted to the positive hydrogen, they bond with the hydrogen, and this carbon then loses an electron and forms a positive charge. It forms a carbocation. An intermediate carbocation is formed because the electrons that were being shared between the two carbon atoms, the double bond electrons, the pi electron cloud, they get attracted to the positive hydrogen, and so this carbon loses its electrons to this hydrogen and gets a positive charge. And in the next step, Br-1, with its lone pairs, it gets attracted to this positive carbocation and eventually bonds with it and ends up forming this molecule over here. So this is the mechanism of this reaction in detail. You have to be very careful with the slight positive, slight negative charges. The carbocations you have to draw. Remember, the arrows represent the direction of the movement of electrons. So everything must be drawn exactly in the right way. Let's move to the next part of the question. The next part of the question is explain fully why 2-bromomethylpropane is the major product of the reaction, while only relatively small amounts of 1-bromo methyl propane are produced. What the question basically means is that if you look carefully, the double bond over here, there are two carbons, and as you can see, the hydrogen gets attached to one of the carbon atoms. Over here, I attached this hydrogen atom to this carbon atom over here. There was a double bond. Electrons get attracted, and the hydrogen gets attracted to this carbon atom over here. It could have been the other way around as well. Let me draw the other molecule. Let's draw it just below over here. So this over here is the other version of the molecule that could be produced. The H getting attached to this carbon atom over here, the first carbon from the left. So it might get attached to the first carbon atom on the left, and the double bond electrons will be attracted to the H, and this carbon would then become positively charged, and Br-1 would then be attracted to this carbocation. So there are two different intermediates that are possible. But intermediate 1, this is more likely to be produced. It's called your major product. And the question is on this: why is this the major product? Why do you get this molecule, this intermediate more compared to this one? Why does the Br gets bonded? Why is the Br always bonded to, or most of the time bonded to the first carbon on the left instead of the carbon on the right? Now the reason is pretty straightforward. If you look at this carbocation carefully, you would notice that this carbon is surrounded by carbon chains. On all three sides, they are carbon chains, and carbon chains have a lot of electrons. For example, this methyl group over here, it has a total of carbon has 6 electrons, 3 from that's 9 electrons in total. This CH3 also has a total of 9 electrons, and there's a CH3 group on this side as well, which also has a total of 9 electrons. So this carbon, positive carbon, is surrounded by almost 27 electrons. So that's a lot of electrons in its neighborhood, and these electrons will be attracted to the positive charge, and the positive charge is going to be neutralized to some extent. It would be neutralized, and if the positive charge decreases, the carbocation becomes more stable, which basically means that it gives it time for Br minus 1 to attach to the carbon. So there's enough time for the Br minus 1 to approach and attach itself to the positive carbon. On the other hand, what happens over here is before Br minus 1 brings its electrons, what happens over here is that the carbocation is very unstable. It's only on one side it's attached to a carbon chain, on two sides it's attached to hydrogens. So there's one electron over here, one electron over here, and this carbon has 6 electrons. So not a lot of electrons in its environment, which means that the positive charge is very, very strong. So it's a strong positive charge, and the positive charge is so strong that it does not let this hydrogen steal its electron. What it does is it takes away that electron and reforms. It ends up reforming the double bond back again. So the double bond is very hard to break because the positive charge is very strong. So if any hydrogen comes in, tries to steal its electron, the positive carbon is going to pull that electron back, and the double bond would be reformed, and the Br minus 1 would not get enough time to attach itself. Over here, the positive charge is much weaker because there are lots of carbon chains. The carbon chains donate their electrons to the positive charge. The positive charge strength decreases, and this positive charge no longer attracts or has attraction for that electron that was stolen by this hydrogen over here. So these electrons, there's very little chance of these electrons coming back and forming the double bond back again. So that gives Br minus 1 the chance to get attached to this positive carbon atom, which is why the reaction is more feasible, and this is going to be your major product. So what you're going to write as an explanation is going to be, so the final answer is that the carbocation in major product has more electron releasing alkyl chain, and this makes the carbocation stable and decreases its charge density, its positive charge density. So the positive charge on the carbocation decreases in strength and makes it more stable. In this question, the question reads: the sequence of reactions is shown starting with an alcohol, C3H7OH. This is propanol. So you're starting with propanol, and draw the skeletal formula of the alcohol propanol. That's the first thing we need to do. So we need to draw the skeletal formula of the propanol. Remember, OH is bonded to the carbon atom at the end, because you would notice that this aldehyde that's being formed, or this carboxylic acid that is being formed from propanol, the OH is right at the end. It must be at the end because the carboxylic acid is formed by the carbon atom at the end. The aldehyde is also formed by the carbon atom at the end. So it's going to be propan 1-ol. Propan 1-ol is you're going to have 3 carbon atoms, and there's going to be an OH group, and there would be 2 hydrogens attached to this, 2 hydrogens attached to this, and 3 hydrogens attached to this. Now we're supposed to draw the skeletal formula. The way you draw the skeletal formula is that the carbon atoms are nodes on the skeletal formula. So that's 1, 2, and so it's 1, 2, and 3. And there's going to be an OH attached to the third carbon atom. So these are the nodes 1, 2, and 3 carbon atoms. And this is going to be the skeletal formula for the molecule. Let's move to the next part of the question, which states that state the reagents and conditions needed for reaction 1. Let's go back and have a look. Reaction 1 is this one. It is alcohol changing into carboxylic acid, which is oxidation. And it's complete oxidation, so it's going to be K2Cr2O7. It's going to be acidified, and the conditions that would be used is reflux. Reflux would help prevent anything from escaping the container, because there's going to be a condenser on top, and in that way the alcohol would get completely oxidized to carboxylic acid. So let's write down the conditions K2Cr2O7, acidified, and reflux, or potassium dichromate 6. Next is state the reagents and conditions needed for reaction 2. If you go back and have a look at reaction 2, reaction 2 is the same reaction as reaction 1, except that the alcohol is not completely getting oxidized. It's getting oxidized to an aldehyde, and it should get oxidized to a carboxylic acid, but the reaction has stopped at an aldehyde. The conditions are going to be exactly the same. You're oxidizing an alcohol, but you're preventing the complete oxidation. What you're doing is you're not using reflux, but you're using distillation, because as soon as the aldehyde is produced, aldehyde has relatively lower melting and boiling points. The aldehyde is going to escape and it can be distilled at the other end. It can be taken out from the mixture. If you don't take out the aldehyde from the mixture, it's going to get converted into a carboxylic acid eventually. So the conditions are going to be exactly the same. They're going to be K2Cr2O7, potassium dichromate 6, acidified, but instead of reflux, you will be using distillation, because distillation would help us remove the aldehyde very, very quickly, and that would be taken out of the container. Let's move to the next part. The next part is we need to name the organic product P, that is the product of the reaction 3. Let's go back and have a look at reaction 3. So there's propanol and there's propanoic acid, and they connect together, and alcohols combine with carboxylic acids to form esters. So I can make that ester over here, and then we're going to try and name it. So I've drawn the propanoic acid, I've drawn the molecule of propanol. How are esters formed? The OH is lost from the carboxylic acid, the H is lost from the alcohol. Let's remove the two, and these two eventually combine with each other and they form an ester. This side is called, the carboxylic acid side is prop, 3 carbon atoms. The alcohol side is also prop, it has 3 carbon atoms. The alcohol side ends with propyl or vial, and the alcohol side ends with OH. So its name is going to be propyl propanoate. That would be the name of the molecule.